sir.
Okay, so the things that I'm expecting you to know are first, matrix multiplication. Everybody knows matrix multiplication, right?
Yes, sir.
Okay. Okay. Then properties of addition over multiplication. Properties of matrix multiplication with addition. Okay, properties of matrix algebra. Specifically, if I want to do a plus b into c, it is ac plus bc, the distributive property, and so on. Okay, fine. Does everyone know, or is everybody comfortable with row transformations?
No, sir, no, sir.
Not so much. Okay. Acha. Inverse by column, inverse by which methods did you have? Inverse by row transformations, did you know that? Do you know it? Inverse by row transformations?
Yes, sir.
Okay. So you must be knowing inverse by adjoint method then? Oh,
Yes.
adjoint method. Okay, fine. ठीक है. It's fine. If you do not know the inverse by row transformations, so that's fine. I think, yeah, okay, I know. NCERT doesn't have inverse by row transformations. They only have inverse by adjoint method. Acha, fifth one, the reduction method to solve the system of linear equations. Yes, that is method of elimination basically. Reduction method to solve system of linear equations. Well, if you do not know or if you are unable to recall, that's fine. I will anyways be giving you quick review of the whole of matrices that we have. So what I have not covered here from determinants is the properties of the determinants. I am not going to cover them here, but what I want you to know beforehand is how to expand a 2 by 2 and a 3 by 3 determinant. Is everybody aware of this? Yes, right. ये है ना सबको पता, एक्सपेंशन ऑफ 2 by 2 3 by 3 डिटरमिनेंट्स होना ही चाहिए, ठीक है, फाइन. Cool. Quick review. What is the definition of a matrix? How can we define it? It is a rectangular arrangement. It is a rectangular arrangement of not only numbers but also functions in certain number of rows and certain number of columns. Okay. A question. A determinant has a value, right? We know a determinant has a value. 4 minus 6. Okay. Does a matrix have a value? Can we equate a matrix with a number?
No.
No. Very good. No. So a value of the matrix is not defined. Value of a matrix is undefined. Okay. Value of a matrix is undefined. Acha. What is element? What is element? Entries of a matrix are called elements. Entries of a matrix are called elements, and everyone knows how to index them, right? Aij refers to the element in the ith row and the jth column, right? You know it. What is meant by order of a matrix? Order basically decides or tells us the size. It is usually specified as mn, where m is the number of rows, the standard letter, and n is the number of columns. What is transpose of a matrix? Anyone? The matrix that we get by interchanging row and columns. Okay? यहाँ तक सबको पता है ना, कोई डाउट नहीं है इसमें. Definition, element, order, transpose. Sorry. Okay. Fine. In matrix algebra, what are the requirements for addition and subtraction? What is the mandatory conditions that the matrices must satisfy for addition and subtraction? A plus B and A minus B is defined only if, what is the requirement? A, B are of same size or same order. Okay, let me put it in that way, same order. Okay, and what is the ijth element of A plus B? It is the addition of the corresponding elements in the two matrices. Okay, so it is to be performed pairwise. Scalar multiplication, is everybody aware of scalar multiplication, multiplying a matrix by a scalar? Yes? Okay. Can anyone give me an example where we use scalar multiplication in some formula? Have you ever used scalar multiplication? Not as a numerical example. Have we used it in any of these formulae? Yes, we have. What is the formula? Recall, if a matrix is invertible or non-singular, what is A inverse? It is 1 upon determinant of A into adjoint A. Correct? 1 upon determinant of A into adjoint A. What is 1 upon determinant of A? It is a number or a scalar. Right? So scalar multiplication appears or pops up there. Right? And how is it done? Okay, let me just take an example. 6 into 1, 2, 3, 4. How does it work? We never leave any element of the matrix. 6, 12, 18, 24. Okay, that is scalar multiplication. Now, this whole subject of matrices and determinants, it comes under a much wider subject called linear algebra. You will definitely study linear algebra in your next year, guaranteed. Okay, and the characteristic of linearity, is this. Suppose we have two scalars k1 and k2, and suppose we have two matrices m and n, okay, same size or same order, I would say. Okay, what does the property of linearity tell me? The property of linearity tells me that, okay, the property of linearity tells me that I can without any hesitation do this. If it is k1 plus k2 into m, I can write it as k1m plus k2. Okay. If I want to do k1m plus n, I can do it as k1m plus k1n. And if I want to do something like this, k1 plus k2 into m plus n, it is k1m plus k1n plus k2m plus k2n. Okay, this is called linearity property. It is also satisfied by differentiation, integration and other stuff. Okay, but that's basically a scalar multiplication and addition combined. Okay, fine. Acha, because you said you already know matrix multiplication, I will not go into details of how matrix multiplication is carried out, but I'll just state the prerequisite. When we write AB, okay, or A into B, the first matrix is called prefactor and B is called post factor, right? Okay, what is the prerequisite? The number of columns in the prefactor should be equal to the number of rows in the post factor, and the answer will have as many rows as in the prefactor and as many columns as in the post factor. Okay, and you know the rows of the first matrix should be multiplied with columns of the second one. I don't know whether you knew this, but whenever we take any row of the prefactor, okay, and any column of the post factor, the multiplications that we perform, they resemble dot product. Have you observed that? Okay, these multiplications actually are dot product. Dot product. They resemble dot product. Because in dot products, what do? We take pairwise products and just add. That's what we do. AI1 B1J, AI2 B2J, AI3 B3J, and we add them. Okay. All right. I have one question for you now. In order to get an element of the product, let us say Cij, how many multiplications do we perform? Can anybody answer that question? To get Cij, how many multiplications are required to be performed?
Depends on the two matrices.
Exactly, it depends on two matrices, but suppose I say that A is m cross n and B is n cross p. So how many multiplications for finding one element? N multiplications. Why n multiplications? Look, when I say that A has m cross n, A is of the size m cross n, do you agree that A is going to have n columns in it? Which means each row of A is going to have n elements in it. When it comes to B, and as I'm saying that B is of the order n cross p, do you agree that it has n rows in it? N rows in it and p columns in it. Which means every column of B is going to have n elements in it. Do you agree? Yes. So it's basically multiplication of a vector of size n, dot product of a vector of size n with another vector of size n cross 1. Just say m. Right? So when we want something I cap plus something j cap plus something k cap dot, the same thing with else. How many products we do? We do 3 products because we are dealing with 3 dimensions. So if our vectors are of dimension n, how many multiplications are we performing? N multiplications we perform. Have you followed this? Okay. So to find Cij we do n multiplications. So what is the total number of multiplications that we do? I'm considering repetitions, but what are the total number of multiplications? It will be MNP. Total number of multiplications is equal to number of multiplications that you do to get one element into the total number of elements that you have. That is MNP. Have you followed this? Everybody?
Yes, sir.
Okay. Rajat, do you understand this? Okay. All right. Okay. The next part is minor, cofactor, adjoint, and inverse. Acha. Let us restrict ourselves to square matrices only. Okay. Let us restrict ourselves to square matrices only. Minors and well, minors at least. Minors are also defined for non-square matrices. We will not go into that. Fine. So suppose I have a matrix A. Okay, suppose I have a matrix A, and let Aij be an element of it. And I want to define its minor. How do I do it? It is a determinant. But how do I get that determinant? Can anybody explain that to me? How do we find minor of any element? Determinant obtained by what?
Deleting the rows.
Yes. By deleting Ri and Cj. You know this, right? Because there was a long silence between me asking the question and you answering it. You know it, right?
Yeah.
Okay, thank you. So minor is a determinant obtained by deleting the corresponding row in the column. Okay. What is the cofactor? How do we find or define rather the cofactor? Yes, please. How do we define cofactor? Minor into something. What is that?
Minus 1 raised to the power I plus j.
Correct. Minus 1 raised to the power I plus j. Acha. How do we define adjoint of a matrix? How do we define adjoint of a matrix? Adjoint of a square matrix is defined as the transpose of matrix of cofactors. Right? Adjoint of a matrix, square matrix, is defined as the transpose of the matrix of cofactors. Has everybody recalled what you had studied in 12th standard mathematics? Adjoint of a square matrix is transpose of matrix of cofactors? Yes. And then comes the main formula, inverse. A inverse is 1 upon determinant of A into adjoint. Okay? You should know this formula. An interesting application of scalar multiplication. ठीक है? यहाँ तक sounds clear है ना? कोई problem नहीं है इसमें. Because most of the MCQs which do not involve properties of determinants, they will be based on matrices being invertible or non-singular, or finding a particular entry of a matrix, or something revolving around inverse. Okay, fine. Yes. Now the main, well, one of the main applications of matrix algebra is solving a system of certain number of unknowns in a certain number of equations. So we generally call it a system. Okay, m linear equations in n unknowns. Can we express it as a matrix product? Yes, we can. Okay. Okay. My first question to you is, does everybody understand what a linear equation is? Or shall I state the general form of a linear equation? General linear equation in n unknowns. Let us say n unknowns. Okay, n unknowns. What is the standard form? The standard form is a1 x1 plus a2x2 plus a3x3 so on till anxn is equal to b. Okay, this is the general linear equation in n unknowns. Now, if you understand that, I can write this as the matrix product a1, a2, a3 up to an into x1, x2, x3 so on till xn equal to b. Now, but I should write it as a matrix. You will quickly understand when we have m linear equations instead of 1, there will be additional m rows below a1, a2, a3, a. Do you follow this?
Yes, sir.
Yes. Now, do you know that a system of linear equations, no matter how many unknowns it has, no matter how many equations it has, its solution can always be categorized into 3 types. Do you know that? Nature of solutions of any system of linear equations can always be classified into 3 categories. It will either have unique solution, or infinitely many solutions, or no solution. Do you know this?
Yes, sir.
See, what does this tell you? This basically tells you that the system of linear equations can never have only 2 solutions. It can never have only 3 solutions, or only for only 10, only 100. No. If it has 2 solutions, you can combine them linearly. You can take their linear combination and form infinitely many solutions. Okay, nature of solutions is this. Now, if at least one solution exists, if at least one solution exists, a system is referred to as consistent. So note that under consistent systems, 2 types of solutions come, or 2 types of systems: systems which only have a unique solution and systems which have infinitely many solutions. All of them belong to the category of consistent systems. And if our system is inconsistent, then it doesn't have any solution at all. Okay, it doesn't have any solution at all. Well, do you know examples, or can you come up with examples where in 2 unknowns, 2 equations, 2 unknowns, systems having unique solution, infinitely many solutions, and no solution? Can you think of 3 such systems of equations having 2 equations and 2 unknowns each? I will give you hints. Look, suppose we want to represent these equations geometrically. It is possible only for 2 or 3 unknowns max, but not beyond that. But suppose I want to represent a system having a unique solution which has only 2 equations in it. I will go for 2 intersecting lines. Sorry. I will go for 2 intersecting lines. Right? I'll go for 2 intersecting lines. The point of intersection is the unique solution. Do you follow this? Okay. Yeah. So what will be the case for infinitely many solutions?
they coincide?
Yes, coincident lines. Coincident lines basically represent infinitely many solutions. And no solution means the lines are parallel. Yeah, lines are parallel. Correct. Now in 2D, the coincident lines is not that convincing. But if we have a family of planes in three variables, then the three planes actually, if they do intersect, either they will intersect at a common point, unique solution, or they will intersect in a single line. And our book is a good example of that. Maybe our answer sheet, where every answer sheet is bent and stapled, that corner point, that corner line can be considered as the line of intersection of all the planes. Okay? Fine. Now see, what happens is, if you have equal number of unknowns and if you have equal number of unknowns and equations, if you have equal number of unknowns and equations, then what happens is, if our system of linear equations is in the form of ax plus b, matrix A becomes a square matrix. Okay, matrix A becomes a square matrix. Now for this square matrix, there are two possibilities. Either it is invertible or it is singular. Okay, either it is invertible or it is singular. Now the system will possess a unique solution only if the matrix is inverted. You know this, right? And what is that unique solution? A inverse into B. Now if the matrix is singular, then we cannot guarantee that the system possesses infinitely many solutions. It may even possess no solutions at all. Do you follow this?
Yes, sir.
You do. Okay. Let me give you an example of that. Okay. Consider the equations, or consider the system 1, 2, 3, 6 xy equal to 4, 8. What is the determinant? Determinant is 0. But the system possesses infinitely many solutions because both equations are essentially one and the same. Do you understand? If I plot x plus 2y equal to 4 and 3x plus 6y equal to 8, they are going to coincide. No, sorry, not going to coincide. This should be 12. My bad, this should be 12. Okay, this should be 12. Now they will coincide. But if I change my matrix of constant terms, if I make it 4 and 8, now you realize that these lines are parallel. Determinant is still 0, but no solutions. So be careful. If our system contains equal number of unknowns and equations, matrix A becomes a square matrix, and if it is invertible, you can find its inverse, then the system's solution is going to be unique. But if it is non-zero, if it is equal to 0, if it is not invertible, if it is singular, the matrix, then the system may have infinitely many solutions, or it may not have any solution at all. That requires further investigation. Okay, one last point before we go to numericals, and that point is regarding those systems of equations where right side is 0 or a null vector. Such systems of equations where no equation has a constant term in it. Do you know what they are called as? They are called as homogeneous systems. Okay, they are called as homogeneous systems. Now the speciality of homogeneous systems is that they are always consistent. Can you tell me why they are always consistent? Let us take an example. Is this system consistent? It is. What is the solution? 0, 0. Right? So why are homogeneous systems always consistent? Because the null vector is always a solution. Look, from matrix multiplication we know that if I multiply a null matrix or a null vector by any matrix, I am bound to get null matrix. Do you agree to this? Yes, so they're always consistent. Homogeneous systems are always consistent, which means the category of inconsistent systems does not incorporate homogeneous systems. Do you follow this? If you don't, please let me know right now. I will explain it a bit in a great detail. You have followed this, right? Homogeneous systems are always consistent?
Yes, sir.
Yes, okay. So if homogeneous systems are always consistent, then under homogeneous systems we have only two categories. Unique and infinitely many. Books do not use these words for homogeneous systems. For unique, they use the word trivial. And for infinitely many solutions, they use the word non-trivial. Now, why trivial? Look, even if you do not write these things in the matrix form and apply the method of reduction on them to find the values of x and y, by just looking at these equations, we can conclude that x and y can be simultaneously 0 and that satisfies each and every equation. So it qualifies to be called as a solution. So every homogeneous system will possess trivial solution. So the main problem in homogeneous systems is whether the given system has non-trivial solutions. And this is where the no solutions category doesn't exist, right? So if we now have a homogeneous system, okay, suppose we have a homogeneous system which has equal number of unknown signed equations given a system of n equations in n unknowns, linear equations of course, which is homogeneous. Now here I can say with certainty what happens if the matrix is singular. Look, Ax equal to null matrix, we know it. If A is invertible, only trivial solution exists. But if A is singular, determinant 0, A inverse does not exist, then non-trivial solutions exist. Have you followed till this?
Yes, sir.
You have, right? Do you people know a theorem called Cayley-Hamilton theorem?
Sir,
Yeah, okay. What about others? No, okay. So could be useful. Hence, I am telling you this Cayley-Hamilton theorem. The general statement of Cayley-Hamilton theorem is for any square matrix. Okay, the general statement of Cayley-Hamilton theorem applies to any square matrix of n cross n. But because we are not going to use any calculator in our exams, I will tell you the statement of Cayley-Hamilton theorem only for 2 by 2 and 3 by 3 matrices. Okay, so first let us consider n equal to 2 case. So suppose we have a matrix A, B, C, D. Okay, this matrix always satisfies. Okay, let me repeat, always. Okay, always. So no matter what A, B, C, D are, real numbers, complex numbers, anything, it is always going to satisfy this equation. Always satisfies the following, okay, the matrix equation. The matrix equation A squared minus A plus D into A plus AD minus BC identity matrix of order 2 equal to null matrix of order 2. It will always satisfy the matrix equation. Okay, now a few things here. A plus D is the sum of diagonal elements. Okay, A plus D is sum of diagonal elements, and this quantity is called trace of the matrix. Sum of diagonal elements of any square matrix is called its trace. Any guesses for AD minus BC? Determinant of A. Okay, AD minus BC is determinant of A, and this also gives us a way to prove that if a matrix is singular, its inverse doesn't exist. Okay, see. Suppose I go to, okay, let's say I call it TR into A plus determinant of A into I equal to null matrix. Okay, now let us suppose that the matrix of A inverse of A exists. So I will say multiplying by A inverse. Multiplying by A inverse, we get A minus trace of A into identity matrix plus determinant of A into A inverse equal to null matrix. Okay, therefore trace of A into identity matrix minus A upon determinant of A is A inverse. Have you followed this till this? Okay, I shifted A and trace of A into identity matrix this to the other side, and then I divided both sides by determinant of A. So this is actually giving me an interesting result, and that result is trace of A into identity matrix minus the matrix A is actually the adjoint. Because what is the formula for A inverse? 1 upon determinant of A into adjoint A, that's A inverse. Okay, let's verify this for a matrix. Suppose I take A as 1, okay, say 5, 2, 5, 2, 9, 1. Well, I'm keeping things simple deliberately. Okay, just a second. Take this as 8, 1. Okay, let's take this as 8, 1. So let's now go to the trace. Trace is 5 plus 2, 7. What is determinant of A? 10 minus 8, 2. According to Cayley-Hamilton theorem, our matrix should satisfy the equation A squared minus the trace of the matrix into A plus 2 times the identity matrix equals 0. Let us see using a calculator if it indeed does that. Okay. Let me change the mode to matrix mode. Matrix A 2 by 2. Okay. 5, 8, 1, 2. Okay. 5, 8, 1, 2. Now what I'll do is I will just do a squared minus 7a. I'll do a squared minus 7. If I get negative to I, the theorem will get verified. Okay. Shift 4, 3, mat a squared minus 7 into shift mat 3. So what am I expecting if right side if I want right side as null matrix? Negative to I. Negative to 0, 0, negative. Okay, so the Cayley-Hamilton theorem is verified. Okay, and it's a useful thing to know. I'll tell you why. You may have seen questions, multiple choice questions, where they suddenly come up with a matrix equation like this. Okay, and you might be wondering how are those people actually finding those quadratic equations in matrices. The way to generate them is using Cayley-Hamilton theorem. Okay, so we have verified this. Now let's see if we can find the inverse of the matrix. Okay, the inverse of the matrix is A inverse is 1 upon determinant of A. Okay, 1 upon determinant of A, that is 2 into the matrix trace of A into I minus A. Now see, identity matrix has zeros here, correct? So if I am subtracting these numbers, then this will become negative 8, this will become negative 1, and the trace of A is what? Trace of A is 7. Okay, so 7 minus A is A11, so that will be 2, and 7 minus A22 of 2, so that is 2, so 7 minus, so that's 5. Okay, have you understood what I did?
Yes, sir.
Okay. Now let's find the inverse of the matrix A. 1, 4, negative half, 2.5. Is that right? Yes. Absorb 1 upon 2 inside, bring in scalar multiplication. So 1, negative 4, negative 1 upon 2, 2.5. Okay, so we have verified that. So don't forget this equation. It's a useful thing to know for 2 by 2 matrices. Okay, let's now discuss the 3 by 3 case. Let us now discuss 3 by 3 case. N equal to 3. Okay, so suppose A is A, B, C, D, E, F, G, H, I. Okay, any 3 by 3 matrix satisfies the following equation. Okay, so if for 2 by 2 it began with squared, for 3 by 3 it will begin with A cubed. So it is A cubed minus trace of A plus E plus I, A squared, plus, okay, now let me first write the things here. See if you can guess what I'm writing there. Minus plus minus determinant of A into identity matrix of order 3 gives us null matrix. Okay, so here I write EI minus FH plus AI minus CG plus AE minus BD. Okay, so in a nutshell, okay, so can you guess what we did here, what I did here? What is EI minus FH? Minor of A. What is AI minus CG? Minor of E. And what is AE minus BD? It is minor of I. Okay, so this is actually sum of minors of diagonal elements. This will be trace of A. Okay, you can also use this equation to generate the inverse. Okay, you can do that, but let me help you out with that here. Multiplying by A inverse and adjusting the terms. Adjusting the terms. What will we get? Okay, so look what I'm doing. I'm writing A squared here for A cube into A inverse is A squared minus trace of A into, now see, it won't be A squared, it will become A plus, okay, let me call this as S, sum of minors of diagonal elements. Okay, let me write it in red color maybe. Okay, let me write it in the red color. And this is going to be identity matrix now, right? Now I'm going to shift this whole thing to the other side and I'm going to divide by determinant of A. Okay. Have you understood the simplification steps here? Okay, now I'm going to give you a homework. The homework is take any 3 by 3 matrix of your choice with each element different. Verify Cayley-Hamilton theorem. Verify Cayley-Hamilton theorem for it. And okay, verify Cayley-Hamilton theorem for it. Fine. So take any non-singular 3 by 3 matrix. See, it's not that this theorem works only for non-singular matrix. No, it works for any square matrix. Okay. Verify Cayley-Hamilton theorem for it first. Number 2, find A inverse using star. Step 3, find A inverse using adjoint method. Okay, and verify your result. Can you do that? Okay, main point, send it to me. Send it to me in PDF. Now, I will not encourage you to use a calculator like I do. Please don't use it. Because in the exam, if you become habitual with calculator, okay, that is a very bad thing for the exam because it's not as friendly as this one, the on-screen calculator. So please do all the calculations by your own. Okay, let them go wrong once because matrix multiplications are known to go wrong in the first attempt. Okay, that still happens with me sometimes, but I can afford to make an error and come back and rectify it. Okay, so please do the square and cube things on your own. Take the matrix as complicated as possible. It will also put you through that situation and you don't want in that situation during the exam. Okay, so you please do that by tonight and send it to me. Any doubt in this Cayley-Hamilton theorem for 3 by 3?
No, sir.
Okay. Acha. Anyone with the definition of determinant? Yes, can anyone give me a definition of determinant? Like a matrix, a determinant is also an arrangement of numbers, but unlike matrices where it is always a rectangular arrangement, in a determinant it is actually something we can call it a square arrangement because it always has equal number of rows and columns. Okay, so we can say that it is an arrangement. It is an arrangement of n squared numbers or functions. It is an arrangement of n squared numbers or functions in n rows and n columns. Okay, it is an arrangement of n squared numbers or functions in n rows and n columns, but till this part of the definition of determinant, we find that this is common with that of a matrix. So what addition should I make to this definition so that it will become the definition of determinant and no longer remain the definition of a square matrix? Anyone? Yes, it is an arrangement which can be mapped to a unique value. So determinant always has a value and that value is always unique. Okay, it never has multiple values. Okay, fine. Let us start with 2 by 2. Let us start with 2 by 2 determinant. The value is AD minus BC, and you may be knowing, may not be knowing, but this particular determinant, let's say A00B, which actually gives us area of rectangle spanned by 3 points: origin, then A comma 0 here, and then 0 comma B here. And if I write down this, if I draw a rectangle, then it is actually the area. Okay, AB is actually this area. Now, is this a coincidence that with the way we have got the other two numbers 0, that we have got this area? Does AD minus BC also represent area? The answer is yes, it does. Okay, so see, point 3. Suppose I take 2 points A comma B and C comma D, suppose, okay, in the xy plane. Then I know that I can construct a parallelogram. What do I know? I know that I can construct a parallelogram whose adjacent sides are given by these two vectors. Okay, which two vectors? The position vectors of the points A, B and C. Okay, position vectors of the points A, B and C. Now, did you know that if I want to find out the area of this particular parallelogram which I have drawn here, then what I need to do is I just need to take the cross product, right? I just need to take the cross product. Now imagine how complicated would it be to calculate this area without knowing the determinant expression. You can still do it. So determinant allows us to actually express the information in a more condensed form. Okay, in a more condensed form. So what is this area? This area is actually ABCD. Well, we know that determinant value can sometimes be negative, but that's okay. We just take the modulus if it is representing area. Is that clear? Okay. Let us now go to a 3 by 3 determinant. Let's now go to a 3 by 3 determinant. You already know how to expand it, right? I don't need to repeat it. Or should I write it for the sake of it? It's okay, fine. Remember, to expand any 3 by 3 determinant, or in general any n by n determinant, we have 2 n ways. Okay, we can expand determinant along any of the n rows or n columns. So how do we expand the determinant? We take every element in a particular row and multiply it by its cofactor. Okay, I hope you know that. So suppose we want to expand the determinant along ith row, suppose. Okay, suppose we want to expand the determinant along ith row. So what will I do? I will take every element in the ith row, ai1, ai2, ai3 up to ain, and what would I multiply it by? I would multiply it by the corresponding, not minus but cofactors. Correct? And then I'll add things. And what will that give me? That gives me the determinant A. Okay, so I can write it in a more compact form as Aij, capital Aij, as j goes from 1 to n. Do you follow this? Yes, what is capital A? Capital A is the cofactor, not the minor. While revising matrices, I have already defined the cofactors for you, so I'm not going to redefine it again. Okay, can I expand it along Cj? Of course I can. Expanding along Cj, I can write the determinant as summation as I goes from 1 to n, Aij, capital A. Again, capital A denotes the cofactor. Okay. Now this is as far as the evaluation of the determinant is concerned in a very straightforward way, But we have got some properties which help us in simplifying the evaluation process of determinants. Okay? Okay, and that is what we call the properties of determinants. Okay. Now suppose the original let determinant of A be a square matrix, and let determinant of A be the original value. Now suppose any two rows or any two columns are interchanged. What will happen to the value of the determinant? Sign will change. Ri interchanged with Rj, change, or same thing is observed when any column is interchanged with other column. Okay. Next, determinant of any square matrix is equal to determinant of its transpose. You already know it, correct? When rows and columns of determinant are interchanged, the value of the determinant remains unchanged. Do you remember this or not? You do. You do. Okay. So, can you tell me what is the determinant of k times A, where k is a scalar? It is k raised to n into determinant of A, where A is a square matrix. See, why does that happen? That happens because when we define scalar multiplication of in matrices, we take each and every element of the matrix and multiply it by that scalar. Okay, but in determinants we actually use this property. Okay, so let's say we choose the third row and multiply every element of the third row by a number k. Okay, then the value of the determinant itself gets multiplied by that. We say we can take the factor common from any row or any column. Okay, now we cannot do this or such an operation for a matrix, isn't it? If I have a matrix, and if I wish to multiply this matrix by k, what will happen? Each and every element of the matrix will get multiplied by k. Yes? And therefore we have to adjust this particular property accordingly. So for matrices it's different, for determinants it is different. Well, if you want to write the same property for in terms of matrices, the determinant of Ka is k raised to n into A. Have you followed this? Okay, point it. If any two rows are identical, or any two columns are identical, then what is the value of the determinant? 0. Okay, the value of the determinant is 0. 0.9. Now there is one more case where this thing works. If any row or column can be written as a linear combination of other rows or columns, then determinant of A is equal to 0. Do you know this property or not? Do you understand linear combination? If you don't, please tell me, I will explain. You don't understand? Yeah, sure. See, suppose I take a 4 by 4 determinant. Okay. And I know that this determinant is 0. Suppose I want to fill these numbers so that the determinant is 0, and I of course don't want this to be 0. Okay, so what can I do is I can build a linear combination. Now what do I mean by linear combination? By linear combination I mean addition and scalar multiplication. Okay, so suppose I choose any scalar. Okay, that's my wish. I can choose any scalar alpha times r1. I can choose any scalar beta times r2. I can choose any scalar gamma times r3, and whatever elements that I get, if I substitute them here, okay, alpha r1 plus beta r2 plus gamma r3 is first element here, second element here, third element here, and fourth element here, this will be 0. That is what I say. If we can write any row or column as a linear combination of other rows or columns, then determinant of A is 0. Okay, now if you do not believe me, let us verify this. Okay, tell me any values of alpha, beta, gamma that you want, preferably non-zero. What values shall we take? Alpha, beta, gamma? Come on. Any three values you tell me. Okay, alpha 3, negative 2, and for gamma 4. Okay, yeah, let's say gamma is 4. Now here is the thing. Let us keep the first 3 rows intact. Okay, let us keep the first 3 rows intact. Okay, now what will I write for the first element there? For the first element I should be writing. Okay, now see, I want to multiply the whole of the first row by 3, but when I'm interested in the first element of the fourth row, I'm okay with 3 into 1 minus 2 into 9 plus 4 into 2. Do you get this? 3, 1, minus 2, 9, 4, 2. 1, 9 and 2 are the elements on the first column, or first elements of the rows, and 3 minus 2 and 4 are the scalar that we have chosen. Have you understood this? That is going to be negative 7. Okay, that is going to be negative 7, and that will sit here. That will sit here. Okay, well, let's repeat this process for second one. Okay, 3 into 2, 6, 8 into negative 2, minus 16, minus 1 into 4 is 4. Oh, sorry, minus 1 into 4 is minus 4. Minus 1 into 4 is minus 4. 6 minus 6. Yeah. Yeah. 16. Yeah. Just checking it. 6 minus 16. That is negative 14. That is negative 14. That is negative 14. Okay, next. 3 into 3, 9. Minus 2 into 7, minus 14. Plus 16. Okay, 9 minus 8. Oh, sorry, 9 minus 14 plus 16. That is 11. That is 11. And last, 3 into 4, 12. Minus 2 into 6, minus 12. Nice. 4 into minus 10, minus 40. Okay. That's minus 40. Okay. Now, of course, we are not going to evaluate this determinant on our own. We're going to use a calculator. Okay, so let's do it. You can also use this tool. It is a handy tool. I don't know whether they have any app or that kind of stuff. Okay. So what are our numbers? 1, 2, 3, 4, 9, 8, 7, 6, 2, negative 1, 4, negative 10, negative 7, negative 14, 11, negative 40. Okay, calculate. See, the result is 0. See that? Yes? So that is the basic property. That is the basic property of determinants, and most of the other properties of them, they emerge out of this. What property is that? If any row or column can be written as a linear combination of other rows, then determinant of A is 0. I hope you understood what linear combination looks like. Linear combination looks like alpha r1 plus beta r2 plus gamma r3 equal to 1. Now it's not that always, all the time, all the rows should be involved. 1 row, 2 rows, 3 rows should be, that's fine. Okay, I hope you understood this. Linear, yes, okay, fine. Then point 10. Operations of the kind Ri transforming to Ri plus Krj or Ci transforming to Ci plus Kcj leave the determinant unchanged. Yes, you know it, right? Operations of the kind Ri plus Krj, Ci plus Kcj leave the determinant unchanged. Do you need an explanation for this from my side?
No, Professor has.
Okay, you know it already. Very good. Rajat, what about you? Okay, and not fine. All right then. Maybe this could be our last revision property. That point number 10. That was point number 10. Point number 11. Splitting the determinants. splitting the determinants. Now this is sometimes useful. Okay, not always, but sometimes this is useful. So suppose we have something like A, B, C plus D, E, F, G plus H, I, J, K plus L. So we can actually split this particular determinant into two determinants of the same order, having first two or the other rows or columns intact. Only the third thing will change. Here it will be C, G, K, and here it will be T, H. Is that clear? Fine. So I think knowing these properties and having understanding a fair bit of understanding of other topics from mathematics, let's say functions or trigonometry, occasionally vectors or differential equations, we can solve problems on determinants. All right. Well, let's make a list of applications of determinants. If you can tell me some applications, that will be good. Tell me the topics in mathematics where we actually make use of determinants. Yes. Sorry?
Vectors.
Yes, in vectors, when we want to find cross product of two vectors, or when we want to find the scalar triple product A bar dot B bar across C bar, we use determinants. Yes, that's one use of determinants. Any other use? Kramer's rule to solve system of linear equations. Any other use? Collinearity of 3 points. Okay, 3 points x1, y1, x2, y2, x3, y3 are collinear when this determinant is equal to 0. Do you know that? Yes. In fact, this emerges out of the area problem, area of triangle. It is half into x1, y1, 1, x2, y2, 1, x3, y3, 1 equal to 0. Well, we usually take the mod here. Okay, we usually take the mod there because area cannot be negative. Okay, now this all stems out because we know that this area is area of the parallelogram. Okay, so if we shift origin to somewhere else, we might require a 3 by 3 determinant to evaluate that. Okay, this is area of triangle, and this can also lead to equation of line. Equation of line 2 points form. Okay, the equation is xy1, x1, y1, 1, x2, y2, 1 equal to 0. Okay, continuing the applications of determinants in coordinate geometry, we can also establish the concurrence of lines. Do 3 lines meet or intersect each other at a point or not? Which determinant are we interested here in? The determinant of the coefficients and the constant terms. A1, B1, C1, A2, B2, C2, A3, B3, C3 equal to 0. And what are the equations of the lines? Equations are AIX plus BIY plus CI equal to 0. I goes from 1 to 2 and then to 3. Okay, these are some applications, and you can also extend them to 3 dimensions to get the equations of planes there. Okay, any other coordinate application, geometry application of determinants that you can recall or remember? Yes? There is an application in pair of straight lines. There is an application in pair of straight lines. And what application is that? That application is, suppose we have this general equation of second degree in x and y. Okay? Necessary condition for the equation alpha to represent a pair of straight lines is AHG. Okay, so it's a symmetric matrix and determinant. Diagonally we write ABC and here we write F. Should be good. Do you remember all these things from your coordinate geometry lessons? Or you did not have pair of straight lines?
The last one, sir.
Yeah, okay, it's not there in NCERT, I agree. It's actually there in the Maharashtra State Board syllabus. Good to know, even if you don't, that's totally fine. Okay, pair of straight lines. Okay, so we have covered vectors, we have covered Cramer's rule, that is system of linear equations. We have covered some coordinate geometry applications. Now, anyone with few more applications, or at least one more? Yes. Finding, or okay, let me put it in this way. Forming a differential equation. Okay, forming a differential equation from its general solution. Okay, from its general solution. Does anyone know this? Let me help you out with okay, a differential equation of second order. Okay, suppose my general solution is C1y1, or let's say C1u plus C2v. Suppose this is my general solution, and in this solution I have two arbitrary constants with me. Okay, I have two arbitrary constants. Now, what will be dy by dx? It will be C1u prime plus C2v prime, and we know if our general solution has n arbitrary constants, then our differential equation has to be of the nth order. So d2y by dx squared will be equal to what? C1u double prime plus C2v double prime. Okay? And then we can actually put all these things together in a determinant. Okay, because see, there are only two constants here, right? C1 and C2. There are only two constants. So, can we have three independent equations emerging out of the only those two constants? No, we cannot. I hope you are trying to get my point. See, there are only two arbitrary constants, and if we look at this system of equations from the arbitrary constants point of view, are we not getting three linear equations in only two unknowns? Yes or no? Okay.
That's that.
Okay. See, what I'm saying is, ignore y dy by dx, u dash u double dash, and v dash v double dash. Look at these equations from C1 C2 point of view. Okay. Now, if I had asked you to solve these equations for C1 and C2, is it correct to say that only two equations are sufficient? That means the third equation is redundant. And what do I mean by redundant equation? It can be very easily obtained from the other equations, right? Which means it is as good as this geometry problem now. Concurrence of lines, same point of intersection of all the three lines. That gives us the coefficient determinant to be 0, and that brings us to y dy by dx d2y by dx squared. Then u prime, u double prime, derivatives of u, and v prime, v double prime, this is equal to 0. Quite often, if this tool is a useful tool when it comes to eliminating arbitrary constants. So because not always it's possible to do it. Okay, is that clear? Yes. Acha. There are also some other applications of determinants in first or second year BSc or engineering mathematics, but I will just stop right here. Other applications also come. You will definitely study them in your higher courses of mathematics. Okay? So those are the applications and other properties, but the main property of determinants is a linearity property that we quite often use in many of its special cases. Okay, like we subtract one row from the other, not changing anything. Okay, fine.